Something is hiding at the edge of our solar system, and we have absolutely no idea what it looks like. Not because we haven't tried to find it, not because we lack the motivation or the technology, but because the place where it lives is so remote, so dark, and so brutally cold that even our most powerful instruments struggle to detect anything meaningful out there at all. We're talking about a region of space so far from the sun that our star, the same one that burns you on a summer afternoon, would appear from that distance as nothing more than an exceptionally bright point of light, barely distinguishable from any other star in the sky. And yet, scientists are almost certain something is out there, something enormous, something that has been quietly, invisibly shaping the outer solar system for billions of years, without ever once making its presence obvious. We call it Planet 9, and the story of how we came to suspect it exists, without a single direct observation, without a photograph, without any physical confirmation whatsoever, is one of the most compelling detective stories in the entire history of astronomy. The mass is estimated to be somewhere between 5 and 10 times that of Earth. Its orbit stretches so far from the Sun that it might take up to 20,000 years just to complete one full revolution. At its farthest point, it could be sitting nearly 1,000 times further from the Sun than we are. That is almost incomprehensibly distant. And yet the evidence that something is out there just keeps building. To understand how you can discover something you have never actually seen, you need to first understand a very old and powerful idea. It's the idea that space is not random. Every object moving through it follows rules, precise, mathematical, completely predictable rules. And when something breaks those rules, there is always a reason. Always. This idea first showed its true power in the early 1800s. Astronomers had been carefully tracking the motion of Uranus, the seventh planet from the Sun, and they kept noticing something was off. Uranus was not following the path that physics said it should. At certain points in its orbit, it would arrive slightly ahead of schedule. At others, it would fall behind. Something was disturbing it, pulling at it from a direction no one could identify, nudging it away from where it was supposed to be. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, decided to work the problem in reverse. If the orbit of Uranus was being perturbed, that perturbation had to originate from a specific location. The gravitational influence had to come from somewhere. So they ran the numbers. They modeled the disturbance mathematically and calculated where, exactly, an unknown planet would need to be positioned to produce the effect they were observing. Then, in 1846, German astronomer Johann Galle pointed his telescope at precisely the coordinates they specified. Within a single evening of searching, he found Neptune, the eighth planet from the Sun, discovered entirely through mathematics before a single human eye had ever looked at it. That discovery permanently changed what astronomy thought was possible. It proved beyond any reasonable doubt that you don't need to observe something directly to be confident it exists. You just need to find the shadow it casts on everything around it. The universe leaves evidence. You just have to know how to read it. The Neptune discovery launched a new obsession. Astronomers began hunting for gravitational fingerprints everywhere, the subtle distortions that a hidden massive body would leave on the orbits of its neighbors. And with Neptune specifically, they thought they had found another one almost immediately. Its orbit appeared to carry a faint wobble. Something even further out was seemingly pulling on it. The hunt was on for whatever was responsible. And in 1930, a 23-year-old astronomer named Clyde Tombaugh found something. He had been systematically comparing photographic plates of the same patch of sky taken days apart, scanning for anything that had shifted position. One tiny speck had moved. That speck became known as Pluto, and for the next 76 years, it was officially designated the ninth planet in our solar system. The problem is that Pluto was the wrong answer. Pluto is extraordinarily small. It's not even the largest object in the Kuiper belt, the broad ring of frozen debris that circles the outer solar system. Its mass is so negligible that it could not possibly generate the gravitational pull needed to wobble Neptune's orbit. And here's the part that really stings. As it turned out, Neptune's orbit didn't have a wobble at all. The effect that had motivated the search in the first place was a measurement error. The instruments of the early 20th century simply weren't sensitive enough to be trusted at that scale. So Pluto was, in a meaningful sense, a fortunate accident, found in roughly the right part of the sky, but for entirely the wrong reasons, based on an effect that wasn't even real. The deeper question, whether something truly massive was orbiting in the outer darkness beyond Neptune, remained completely unanswered, and it would stay that way for the better part of a century. Starting in the early 1990s, improved telescope technology finally gave astronomers a real look at the outer solar system for the first time. What they found out there was staggering. The Kuiper belt, the vast disk of frozen rock and ice that extends far beyond Neptune, turned out to be enormous in a way no one had fully appreciated. Potentially hundreds of thousands of objects larger than 100 kilometers across, billions of smaller ones. We had been essentially blind to the majority of our own solar system's real estate, but the sheer number of objects was not the most interesting discovery. What really got people's attention was the way certain objects were moving. Among the most distant Kuiper belt objects, the ones with the longest and most elongated orbits, astronomers began identifying something that had no obvious explanation. Their orbits were clustered. Several of them shared strikingly similar orbital orientations that shouldn't exist if these objects were simply distributed randomly around the system. Chance distributions spread things out. These were bunched together, pointing in similar directions, tilted at consistent angles, lining up in a pattern that looked far too organized to be coincidental. And then there were the even more extreme cases. Objects found to be orbiting perpendicular to the flat plane of the solar system, swinging in enormous arcs over and under the sun. Objects traveling in the retrograde direction, moving opposite to every other known body in the entire solar system. These weren't minor statistical oddities. These were dramatic, almost theatrical deviations from what you'd expect in a system that had no major undiscovered member lurking somewhere in the dark. Something was clearly at work out there. The question was, what? In January 2016, two planetary scientists at the California Institute of Technology published a paper that immediately became the biggest story in planetary science in years. Mike Brown and Konstantin Batygin had spent a long time studying a specific cluster of distant Kuiper belt objects, and what they found in the data was difficult to explain away. The probability of the orbital alignment they observed occurring purely by chance was estimated at somewhere around 1 in 1,000. That's not impossible, but it's the kind of number that demands an explanation. Their proposed explanation was the same one Leverrier had applied to Uranus nearly 2 centuries before. There is a large undetected planet out there, and its gravity is systematically steering these distant objects into the arrangement we observe. The math suggested this planet would need to be between 5 and 10 times the mass of Earth, substantially bigger than anything previously known to orbit beyond Neptune. Its orbit would be dramatically elongated, swinging from a few hundred times the Earth-Sun distance at closest approach to perhaps 800 to 1,000 times that distance at the far end. A single orbit could take anywhere from 10,000 to 20,000 years, and the orbit would be tilted relative to the plane of the solar system by around 15 to 25 degrees, explaining why it hasn't shown up in any previous survey. They ran it through computer simulations. They modeled the solar system in its early, chaotic state, and then ran it forward through billions of years. When Planet 9 was included in the model, the distant Kuiper belt objects settled into exactly the pattern we observe today. When it was removed, the pattern fell apart. The simulation alone put the probability of Planet 9's existence at better than 99%, according to their estimates. Assuming Planet 9 is real, it brings an immediate problem. That far from the Sun, the density of material in the early solar system was far too thin to assemble a planet of that mass. The building blocks needed to form something that's substantial simply weren't concentrated enough out there. Planet 9 almost certainly did not form where it currently orbits. The most widely supported idea is that it formed much closer to the Sun, somewhere in the neighborhood of the region now occupied by Saturn and Uranus. During the turbulent early period, when the giant planets were migrating significantly through the solar system, Gravitational interactions between the large planets during that era were chaotic and violent. It's entirely plausible that during one of those reshufflings, a forming planet was thrown outward with enough velocity to end up on an extremely elongated orbit, but not quite enough to escape the Sun's gravity entirely. Flung to the outskirts, trapped in a distant and eccentric loop, never able to fall back in, and never able to break free. The second possibility is considerably more dramatic. Stars don't form in isolation. They form in dense clusters, packed closely together in their early years, before those clusters slowly disperse over millions of years. During that ancient crowded period, stars are close enough to gravitationally influence one another, and potentially to exchange planets. It is theoretically possible that Planet 9 was originally orbiting a different star, was ejected from that system, and was then captured by our Sun's gravity during the brief window when the two stars were close enough for that exchange to occur. A rogue planet pulled in from interstellar space and locked into orbit around our star before the stellar neighborhood spread out and made such encounters impossible. In either case, what Planet 9 would look like up close is not an encouraging picture. A frozen, airless, geologically dead world, dense rock and metal compressed under tremendous pressure, coated in frozen gases and ices, baked by nothing. No magnetic field worth noting, no geological activity, no internal heat left to speak of. Something darker and colder and more inert than anything else we have ever found in the solar system. If Pluto seems bleak, Planet 9 would make Pluto look welcoming. Not everyone finds the evidence convincing, and that is worth taking seriously. The same observational bias that accidentally produced Pluto could be operating here too. Brown and Batygin were explicitly searching for evidence of a large distant planet, and the objects whose orbits form the basis of their argument were themselves discovered through telescopes that do not survey the sky uniformly. Telescopes point at specific regions that are easier to observe, or that previous surveys flagged as productive. That means the population of known distant Kuiper belt objects is not a random sample. It's a biased one. And a biased sample can produce clusters that look statistically significant but actually just reflect where the telescope happened to be pointing. Several researchers have re-examined the dataset using more complete survey catalogues, and when they account for that observational bias, the apparent clustering weakens considerably. It doesn't disappear, but the odds of it occurring by chance improve significantly, enough that some scientists argue the Planet 9 hypothesis is premature. There are also alternative explanations for the orbital behavior that don't require a planet at all. One of them is almost more unsettling than the planet itself. A small primordial black hole, formed in the first chaotic seconds after the Big Bang, before stars even existed, could in principle produce the same gravitational effects from the same distance. These objects are hypothetical, and if they exist, they would be extraordinarily small and dark, completely invisible to any conventional telescope. The odds of one being trapped in a stable orbit around our Sun are very low, but the theory has not been disproven, and there is a simpler possibility still. Maybe gravity at these extreme distances behaves in ways that our current models don't fully capture. Newton's laws of gravity were developed based on observations of objects that are close together on a cosmic scale. Everything beyond Neptune is essentially uncharted territory for our gravitational models. It's possible that effects which look strange to us are simply what normal gravitational dynamics look like at thousands of astronomical units from the Sun, and that there's nothing unusual to explain. This debate may finally be approaching its resolution. The Vera C. Rubin Observatory, located on a mountaintop in northern Chile, began full scientific operations in 2025. It is built around the largest digital camera ever constructed for an astronomical instrument, a 3.2 billion pixel sensor attached to a telescope designed to capture the entire visible night sky every 3 days. That survey will continue without interruption for a minimum of 10 years. What that produces over time is a comprehensive time-lapse record of every detectable object in the sky. Anything that moves will reveal itself. A comet approaching from the outer system will gradually shift against the background of fixed stars and show up in the data weeks before it becomes visible to smaller telescopes. Near-Earth asteroids on potentially dangerous trajectories will be identified years earlier than our current systems can manage. Interstellar objects, visitors from other star systems, like the object now known as Oumuamua, will be detected soon enough after entering the solar system to actually study them in detail. And if Planet 9 is out there, it will move. It will move slowly. An object at that distance covers very little angular distance in any given year, but slowly is not the same as undetectably. Over the course of Rubin's decade-long survey, even a planet sitting 600 or 700 astronomical units from the Sun would shift position by a measurable amount relative to the background stars. That shift, accumulated over thousands of nights of imaging, would produce a signature in the data that cannot be mistaken for anything else. This is not passive observation. It is a systematic, structured, and unprecedented survey of the sky, conducted at a level of resolution and completeness that no previous generation of astronomers has had access to. If Planet 9 is real, Rubin should find it. If it isn't, Rubin's data will make that clear too, and astronomers will be forced to find a different explanation for what is happening at the solar system's edge. Here is the thing worth sitting with, regardless of which way the answer goes. If Planet 9 exists, it means our solar system has a major member that we have been completely unaware of for the entire history of human civilization. Every map we have ever drawn of where we live in the universe has been missing something significant. And depending on which origin story turns out to be correct, we may be sharing a solar system with a world that started its existence orbiting a completely different star, the first confirmed object of interstellar origin permanently bound to our Sun. The implications of that alone would be staggering, extending well beyond planetary science into questions about how planetary systems interact with each other and whether the exchange of material between star systems is a common feature of the universe. If Planet 9 does not exist, that answer is equally significant. It would mean the gravitational effects we are observing at the edge of the solar system have a different explanation, one that might require revisions to our models of gravity or of Kuiper belt dynamics, or of how biased our observational surveys have been. There is no version of this story that ends quietly. We have a deep and persistent tendency to assume we understand our own solar neighborhood. 8 planets, a few dwarf planets, some comets and asteroids, all catalogued and accounted for. But our knowledge of what lies beyond Neptune is genuinely thin even now, in the 21st century. The volume of space between the outer planets and the outermost edge of the Sun's gravitational reach is vast to a degree that is difficult to appreciate, and we have surveyed a tiny fraction of it. The outer solar system is not a finished chapter. It is a largely blank page that we are only just beginning to write on. And with Rubin now scanning the sky 3 times a week, every week, year after year, we are almost certainly on the verge of finding out what is actually out there. The answer is coming. We just have to wait for the sky to show us.